Thank you for coming to my presentation. So today I'm gonna talk about a collaborative project that I conducted with other researchers at Harvard and in the National Institute of Environmental Health. I was approached by this investigator at the National Institute of Environmental Health who had been reviewing several papers conducting mediation analysis in the field of environmental epigenetics, and she was very concerned about potential false positives. As I will illustrate today, there are strong signals showing that epigenetic mechanisms can explain the harmful effect of environmental factors on health. However, it seems like if we consider many of these epigenetic factors and consider mediation analysis, trying to assess whether these epigenetic factors are mediators, and we had to sum up all the mediation effects, we would sum up a percentage that is much more than 100%. And so this talk is about asking this question. Are these epigenetic factors and epigenetic traits actually mediators, or just strong biomarkers of imperfectly measured environmental exposures? I won't have a lot of time to delve into what an epigenetic trait is, but I will introduce and give some background for people who have never heard about epigenetics. These are the lists of collaborators who all contributed. I couldn't directly apply the methods to the data itself because they stayed in Norway. So thanks to Christian Page, Sarah Rees, they all applied the methods on this data. And I thank them for that. So many studies report that epigenetic marks, that is, modifications in the way our DNA is regulated, and here we will focus on DNA methylation, that is when metal groups attach to the DNA so that they either block the expression of certain genes or encourage the expression of certain genes. These epigenetic factors are related to several health outcomes. And it has also been shown that those epigenetic factors are also highly modulated by environmental exposures. In these studies, timing of exposure is critical, as well as the timing and tissue where we measure the epigenetic factor. Now, this term, epigenetics, is very popular in the press to directly indicate the environmental effects that can be molecularly explained on health. This is a table that summarizes some of the findings that have been clearly established on the relationship between some of the most important environmental toxicants, several epigenetic traits, DNA methylation is the most well studied, and several health outcomes across, cancer, cardiovascular disease, and others. The question of whether the environmental effects are mediated by epigenetic traits can be effectively represented in this directed acyclic graph. This is a very simple graph that will need to be populated by other variables, but this explains the structure of the scientific question at hand. Our factor A is an environmental exposure of interest. Our variable Y is the health outcome of interest. And M is a factor, here an epigenetic factor, say DNA methylation, that lies on the pathway between the exposure A and the outcome Y. This graph assumes that the exposure temporally precedes the mediator and the outcome, and that the mediator temporally precedes the outcome. It also assumes that there are two ways through which A can affect Y. A can affect Y by changing levels of M. We see a direct arrow from A to M and M to Y, as well as by acting through other pathways that are independent of the hypothesized one. This is the direct effect. whereas the former is the indirect effect through M. So it seems very intuitive that we could decompose in some way the effect of A on Y in these two paths. However, in environmental epigenetics that is conducted typically using observational data, there are several challenges to achieve this decomposition. First of all, there are ethical considerations, so we have to use observational studies mostly to assess environmental effects. And the other big problem is that in order to observe the outcome, we might need long induction periods that are needed for the exposure to have an effect on the outcome and also to modify the epigenetic factor. In most of the studies, there is a huge issue of reverse causation, that is, environmental exposure and epigenetic trait are measured at the same time, and this poses challenges for the causal interpretation. What would be optimal would be to have several longitudinal measures over time of both the exposure into the environment and the epigenetic factor, but this is not always possible. And the other issue is the tissue specificity. That is, depending on the health outcome, you might want a specific tissue where you measure the epigenetic factor, but at times it's not possible to get that tissue. The case study that motivates my methodological work concerns the effect of maternal smoking during pregnancy and child birth weight, potentially mediated by the epigenetic factor DNA methylation measured in cord blood. And this is exactly the papers that my reviewer, Stephanie London, had reviewed, and she reviewed several papers considering different epigenetic markers, finding like that for each different epigenetic marker, they were explaining 30%, 50% of the effect. And if she were to sum all them up, it was impossible that each of these epigenetic factors could have all explained such a large amount of the effect of smoking. So she says, there might be some problem here. Methodological issue, help me find out what that might be. So I will go in depth in explaining how certain investigators went about explaining the effect of maternal smoking on child birth weight through DNA methylation of a certain specific gene. Cooper et al. Considered the population in the Dutch gecko cohort, and they did not restrict themselves to a specific gene, actually. They conducted an epigenome-wide association study to determine whether there were any epigenetic traits that could be, and the demethylation traits in particular, that were both associated with the smoking status of the mother, as well as associated with birth weight. How they conducted this study? First of all, they had to account for the multiplicity. And currently, there's still a big gap in the literature of how you study direct and indirect effects when the mediator is a high-dimensional factor. So they used what is currently standard practice, that is, conduct a mediation analysis for each single epigenetic trait, for each site, and then just accounting for multiple comparisons. However, this approach is definitely not optimal because it doesn't account for the correlation among the loci, and it could be actually both conservative or non-conservative. So, but that's what they did. So here I provide the flow of their study. First, they restricted themselves only with respect to the top 35 CPG sites that were found to be associated with smoking. So first, they want to see, of the demethylation of these loci, which of these loci are really predictive of smoking status. 35 were selected. And they were selected using the FDR correction and considering an FDR less than 0.05. Of these 35, they found that 8 CpG sites, all present in one gene, the insulin growth factor gene, which kind of makes a lot of sense, were also associated with birth weight and displayed a strong indirect effect. So 8 in their cohort. Then they went on, just focusing on these 8 loci, so like considering 8 mediators, and they conducted again the mediation analysis in 2 separate cohorts, ALSPAC and Generation R, to replicate the findings. They were able to replicate the findings for 3 CpG sites in this insulin growth factor gene. And they reported that DNA methylation could have explained between 12% and 19% of maternal smoking on birth weight. So out of the whole scan of the genome, they found a robust signal for 3 CpG sites in one gene, insulin growth factor gene. Then there were other studies instead that conducted similar EWAs and reported in different genes signals that showed approximately the same or even larger proportion mediated. The proportion mediated is the proportion of the total effect of smoking on birth weight that is explained by the mediators of interest. Here I have the final comment that motivated my work. That is, the authors in their study did not evaluate the potential bias due to misreport of smoking status. So we know that mothers are less likely to report to be smokers. Moreover, a very crude measure of smoking status was considered, just a binary variable of whether the mother was smoking or not, was a smoker or not. So our question is it possible that this study is confusing the CpG sites as being mediators, but really maybe they are just biomarkers? Because DNA methylation is a measure that is really precise and continuous, that is highly predictive, that really highly predicts smoking status, and actually sometimes now in certain studies they use DNA methylation to classify a person as a smoker or not. That is even found to be better than self-reported smoking status. So could this be due, could there something about this that leads to inflated mediated effects? So the goal of my presentation now is to define more formally what these direct and indirect effects are, describe the problem of exposure misclassification and its impact in mediation analysis in terms of bias and type 1 error, and then apply the methods and our intuition about our results to a new data, the MOBA study cohort in Norway. So some notation to define our effects. We define Y as being our birth outcome, which is birth weight. A is a binary predictor, maternal smoking status during pregnancy. M is a continuous mediator, cord blood DNA methylation, which is potential on a pathway between A and Y. And we denote now with C a set of covariates that are needed to adjust, we need to adjust for in order to warrant causal interpretation of our analysis. These are the potential outcomes that we consider. Y subscript A is the birth weight for each individual. If we were to intervene, setting the smoking status, say, to smoker or non-smoker. So little a is a particular value at which we set the smoking status of the mother, can take 2 values in our case, either 0 or 1. Y subscript AM is instead the birth weight that we would observe if we could intervene by not only setting the exposure level to a certain level little a, But also we could intervene on DNA methylation somehow, if we were able to control it with some magic pill that fix it at a certain level. And we also define M subscript A as the DNA methylation level of a certain CPG site when intervening to set A to little a. So in this presentation, I won't focus on the high dimensionality of the problem, which is an extension of the work I'm presenting today, just because I think it's more important to get the idea in the one-dimensional space, because it's just going to be worse in the high-dimensional space. So here I define the direct and indirect effects if we were interested in a single mediator, M. And this is the formal definition that is non-parametric and written in terms of potential outcomes. And here I just give you the intuition behind these definitions. So this definition depends on the potential outcome Y when we intervene in a special way on the first subscript, which always denotes the exposure A, and the second subscript, which always denotes the mediator M. In the first effect, you see that the outcome has the same mediator level, which is M subscript 0. That is, we think about the impact of an intervention that sets the smoking status at two conditions, either absent or present. But while we set the exposure to different levels, we also intervene on DNA methylation in a particular way, keeping it fixed under both exposure levels. Why is it important to keep it fixed? Because if we wanted to capture the direct effect, the exposure has to operate through pathways that don't involve M. So how we achieve that? By blocking M, by leaving it fixed. We forced it fixed, so that if smoking status changes, this change has to operate through pathways that don't involve the mediator because it remains fixed. So this is the intuition behind this definition, which is the effect of the exposure on the outcome when the mediator remains fixed at the level that we would see if the mother was not a smoker. Then instead, the indirect effect wants to capture the opposite, that is, the effect of the smoking status on the outcome that could only change the mediator. So what if smoking could only change DNA methylation of a certain trait and nothing else? What would be its effect on the outcome? How we formalize this? By changing the mediator from its natural level in the absence of smoking to its natural level in the presence of smoking. So M subscript 0 is going to be different from M subscript 1 only if smoking has an effect on M. Otherwise, M0 is going to be equal to M1. First thing. This is the first arrow between A and M. In order to have a pathway, we need to have that M0 is different from M subscript 1. But then, in order to have an indirect effect, we also need that the mediator changes Y. So the outcome Y when M is set to M1 has to be different from the outcome Y when M is set to M0. Given this, the exposure smoking can only operate through M. So it's only M that can change here, not the exposure. So that's why the first subscript remains fixed. So I know this is not easy if you have seen this for the first time, but this is a way we can formalize these pathways using the potential outcome framework. And it's very convenient because we can show that the sum of these two non-parametrically defined effects gives the total effect, the effect of smoking on birth weight.
Linda?
Yes?
You've considered two kinds of covariates, C1 and C2.
Ah, yes. Because
is it important in a way, and you're assuming that there's no interaction between these two kinds of covariates, Does it change something if there is one?
Yes, it would. I mean, it definitely matters when we set now models to recover these effects. But let me first explain why I separated them. I just thought that there are settings here that C1 is a confounder that affects the exposure, the mediator, and the outcome. So these are factors that precede the exposure. These are baseline covariate. So they could affect the exposure, the mediator, and the outcome. They would not be an issue if the exposure was randomized, because we would have no arrow from C1 to A, so we would not need necessarily to account for them if we were in a randomized study. We could adjust for them because they might improve precision of the model, but they are not needed for ensure causality. C2, instead, are potentially post-treatment, post-exposure covariates, which affect the mediator and the outcome. So here we encode a very important assumption that there's no arrow from A to C2. That is, we assume that there are no confounders of the mediator-outcome relationship that are mediators themselves. This is very problematic because it's almost never the case that this C2 is independent of A. And so now there are several methods that are being developed to overcome this limitation, because direct and indirect effects cannot be identified if there is an arrow between A and C2, and so it's a big assumption in this DAG that we are excluding this arrow. However, if this arrow is present, although these counterfactuals cannot be recovered, cannot be obtained from observed data, so know that these are missing. We don't know what these potential values are. It's a huge amount of missing data when we think about causal inference and in particular mediation analysis. But here, that brings me to discuss what are the identifiability conditions, that is, under which assumption we can hope to use observed data to estimate these effects. And these are encoded by accounting for these C1 and C2 variables and assuming that there is no arrow from A to C2. This is the simplest possible models that we can set up to estimate direct and indirect effects, and these are the ones that I will be considering because even these simple models can be biased in the presence of exposure misclassification. So in order to conduct a mediation analysis, we need to establish a relationship between the mediator and the exposure, and between the outcome, the mediator, and the exposure. So typically 3 models are specified. A model that here everything is continuous, and we use linear models, so the simplest thing possible. Although we know we could extend it to allow for nonlinearities and use more general link functions. But let's consider the case when we have a simple linear model. A linear model that relates the exposure A to the mean of the mediator M, accounting for the covariance C. We have a model for the outcome Y that conditions with respect to the exposure, the mediator, and the covariance. And also we have our model for the total effect that is similar to equation 2 but doesn't adjust for the mediator M. In this very simple formulation, we can define the direct effect as θ1 from model 2, which is the association between A and Y. Once we control for M in the model, so that we only capture the association between A and Y when M is fixed. And this is also represented in this graph. This is basically this arrow, θ1. And the natural indirect effect, in particular, is also called the product method indirect effect, that if these models are correctly specified, coincides with what the causal inference literature would obtain, are the products of, very intuitively, 2 coefficients. The coefficient that describes the relationship between A and M, and the coefficient θ2 from model 2 that estimates the relationship between M and Y. There is also an alternative estimator that we could consider, which is the difference method indirect effect that we can obtain by using the effect decomposition property, which tells us if we estimate the total effect, which is θ1 dagger from model 3, and we estimate unbiasedly the direct effect from θ1 in model 2, we can obtain the indirect effect as the difference of these coefficients. And it has been shown that if the models are right and the outcome and the mediator are Gaussian random variables, these two estimators, one is a product and the other one is a difference, coincide magically. I mean, one would expect that the distribution of a product would be very different from the distribution of a difference, but in large samples and when everything is Gaussian, it happens. Of course, when normality does not hold, all this breaks down and we have two methods that yield the different results, so this is problematic. So there are several challenges, even when we use this simple model to assess mediation, but we focus here on the problem of measurement error. And yes, yes.
In red, is it really the absence of exposure mediator or outcome mediator?
Exposure mediator, because basically it has been shown that these estimators are really wrong when you have an exposure mediator interaction. And all the things I'm discussing today have been extended to the case when we have an exposure mediator interaction, but the formulas become very complicated, so I decided to focus on the case without, so to illustrate the method more easily. But there are results for more complex models. I just think it's easier to have an intuition on the case where we use these models 1 to 3. So here we're talking about the problem of measurement error in an exposure. So what has been done in the literature? It has been considered the case of a mediator measured with error, making some very standard assumption, in particular the assumption of a classical non-differential measurement error. What do we mean by classical? Typically, classical restricts what can be the moments of the error, and also non-differential is the assumption that the way a person reports the variable is independent of the latent true nature of the variable, which definitely is not the case for us. And typically they consider linear models. Is it also often stated in the literature, and actually Kuppers et al. At the end of their paper, they say we could have measurement error, but this means that with measurement error, our estimate could just be conservative, because we know that measurement error typically dilutes effects, and therefore our estimate could be conservative. So that's typically what people conclude when measurement error is a potential issue. However, we showed in previous work that this intuition may not hold in several settings. For example, when the mediator is measured with error and it interacts with the exposure. So the model 2 is misspecified and there is indeed an exposure-mediator interaction. If the mediator is measured with error, we could observe overestimation of the indirect effect rather than an underestimation. Or, of course, when exposure or confounders, as we will show today, are measured with error, we could have inflation of the effects rather than underestimation of the effects. And it has also been shown when a polytomous mediator is misclassified, we could observe overestimation rather than underestimation. Things that have been completely neglected in mediation analysis is what is the validity of the type 1 error of tests of mediation when the variables are measured with error. And the other thing that is even more philosophical is what is the impact of coarsening or ill-defining variables involved in a mediation analysis, which in the end I think here was the worst problem, was not actually self-report, but was mostly also the coarsening. So there are several layers of problems when you think about measurement. So this is our the type of analysis that Cooper and al. Conducted. they fitted these two models that I just described, and they estimated direct and indirect effects using those very simple formulae. But they didn't acknowledge that the exposure is measured with error. So let me introduce the assumption on the misclassification. The exposure A is the true latent binary status. A star is the self-reported smoking status, which is the truth plus an error, U, that is categorical. That is, it can take value -1, 0, or 1 with a certain probability that we can be, and the distribution of U can be completely characterized if we know what is the prevalence of a star and the sensitivity and specificity. So in our study, we didn't have replicates. So this sensitivity and specificity could be studied if we had many measurements or a gold standard, that is for certain women, we exactly measured throughout pregnancy what was their smoking status and try to recover what this measure might be. So if they are not available, what we can do is a sensitivity analysis, thinking about a range of plausible values of sensitivity, which is the probability of reporting of being a smoker given that the woman is a smoker, and specificity, the probability of reporting of not being a smoker given that the mother is not a smoker. So now we see that the misclassification error depends on the latent true exposure. So we have a problem of non-differential misclassification. We also assume perfect specificity because we expect that if a mother is not a smoker, is always gonna say that she's not a smoker. So specificity can be set to 1, which is perfect. However, sensitivity can be imperfect in our study. The critical feature of our study is that DNA methylation has been used to classify women as smokers or not. So it's a strong and precisely measured biomarker of an imperfectly measured and coarsened exposure. And indeed, we are actually fitting this model where the true exposure A is replaced by A star. And we can show that if A is not observed and we replace it with A star, the estimators of the mediator and outcome regressions are not going to be consistent. So we can obtain the probability limit of our estimator, of our biased estimators of the direct and indirect effects. And this is what we did. But we went in stages. We know that to estimate direct and indirect effects, these are the ingredients, just 3 parameters. So if we are able to recover the bias due to exposure misclassification for these 3 parameters, we are all set. So that's what we did. That was very easy. And in particular, this is the probability limit for the association between A and M, which can be shown to be an underestimate. So if you think that Kuppers et al. Selected the top 35 CPG sites that were associated with smoking, most likely this is an underestimate, and maybe there are many more CPG sites that are actually associated with smoking, because we are diluting this effect. So, okay, great. It seems like then we might be underestimating one component of the mediated effect. And the bias depends on the covariance between A star and U, which is an amount of measurement error, because the covariance can be written in terms of parameters, sensitivity and specificity, and factors that can be obtained. I mean, basically, sensitivity and specificity are the only unknowns here, because we could rewrite the probability of the true A equal to 0 based on information on sensitivity, specificity, and the prevalence of observed A in our population. Then it depends on how this term delta M A star, which is an element of the diagonal of the inverse of the variance covariance matrix, which depends, of course, on the variance of A, but also on the correlation between A and everything else that is in our model, which we know are going to be highly correlated, because in mediation analysis, everything is that in the model is because it's highly associated. And then the true underlying relationship. Then, when we go about studying the outcome regression parameters, we have two of them that we need to study. And then we see, in particular, that θ1 is the parameter of A, of the association between A and Y. This again is going to be diluted. So we are going to dilute the direct effect. However, and this is what causes the problem, the relationship between the mediator and the outcome, so θ2, is going to be overestimated. And this is the problem here. And what is the bias made of? The bias of the relationship between θ2 and Y depends on whether A and M are correlated, the magnitude of the error, and the magnitude of the effect of A on Y. What does this mean? That the bias of M depends on, first, how strong is the relationship between A and Y, but also how strong the relationship between A and M. So this is basically, the more is the effect of A on Y, the more is the effect that M can steal from A. And how much can it steal? It can steal this effect if M is strongly related with A, that is, can act as a proxy for A. So if M is a strong biomarker, it can act as being the exposure itself and steal its effect on the outcome away from the true outcome. So this is what's happening. So it's nice to work with mediators because they should be related to the exposure, but they shouldn't be too collinear. Otherwise, you will never be able to disentangle what is causal and what is just an underlying factor that is just very predictive. So this is basically why I show that the association between M and Y is going to be overestimated. So we have one arrow here that's going to be underestimated, but this one is going to be overestimated. But note, it's not going to be overestimated if there is no association between A and M. So this is the bias that we can then derive for the direct and indirect effects. And the bias of the direct effect is very easy to see. It's just an underestimation of the direct effect. However, the bias of the indirect effect can go in both directions. Can either be an overestimate or an underestimate. And interestingly, it's going to be 0 if beta 1 is equal to 0. Okay, now I just want to think with you a little bit about what it means to test that the indirect effect is 0. This is not a trivial test. This is a test that involves, so let me go back to this, testing whether two parameters, beta 1 and theta 2, are equal to 0. That is, a test for a null indirect effect is a test for a composite null hypothesis where the null can be achieved under three conditions. 1, beta 1 is equal to 0 and theta 2 is different from 0. Second option, beta 1 is different from 0 and theta 2 is equal to 0. Third, both of them are equal to 0. What messes up this case study is that we might be in the null hypothesis where beta 1 is different from 0 because we know that the mediator is a strong biomarker, but theta 2 is equal to 0. And we falsely find an association because M is stealing the true effect from A. The problem is exactly this, that we can be under the null of one of these three null, the null in which beta 1 is different from 0 and theta 2 is equal to 0, but still under the null we have bias. And this one key feature of the hypothesis testing, that for the type 1 error to be preserved, the estimator has to be unbiased under the null. Here we are violating this assumption that under the null our estimator will unbiasedly estimate the effect, that is 0. Here, our bias that we derive shows clearly that we could be in the setting in which θ2 is equal to 0, but still having a non-zero bias, so that the indirect effect could be non-zero under the null based on this estimator. So that's why not only we are going to have bias, but if we are in that specific case of that second condition under the null, which indeed seems to be the case potentially in our example, we will also have improper tests, tests that do not preserve the type 1 error. So we have done extensive simulation studies which shows that even in certain cases you could have type 1 errors of like higher than 50% easily. And this is something that needs to be assessed. So the main take-home message of this presentation is there are several software for measurement error that you can apply. This should be a routine practice in these epigenetic, environmental epigenetic studies, where we know that it's very hard via self-report to obtain measurements of the exposure.
There are sensitivity analysis, you mean?
Yeah, exactly. And this is one that I am explaining for, and we chose this for this paper because there is a very nice package that applies this method that is called the simulation extrapolation method, developed by Carroll et al., which can be directly applied to our regression models to obtain, assuming different sets of values for sensitivity and specificity, a new corrected estimate of the parameters, and therefore use these new parameters as estimated to obtain the direct and indirect effects. Here I give briefly a representation of what this method does. In our case, we have a single sensitivity analysis parameter, which is sensitivity, just not to be confused. So the sensitivity is our parameter, because specificity is set to 1, because we think that mothers won't lie if they are non-smokers. What is the idea behind this method? First of all, we set certain potential values that the sensitivity parameter can take. The optimal value is 1, and then we have a range. Let's say that we have a certain point estimate, which can be one parameter from our outcome regression, say θ1. And in the y-axis, we have what is the value of that parameter estimate. Say that this point here is our parameter estimate that takes a value slightly higher than 1. And we make an assumption. Let's say that sensitivity is 0.9 in this study. So we set sensitivity. Then the second assumption we need to make is what is the relationship between the true parameter and the parameter estimated with misclassification. And here we don't know what is the true relationship. In fact, we should use this approach considering different functional forms. Here I'm plotting it assuming a quadratic relationship. Now that we have these two ingredients, a level of sensitivity at the observed value and a function that describes the relationship, what this method does is adding measurement error to the data, and for each new error that you add, estimate new effects and extrapolate, learn about what this function might be. You estimate this function, and then you extrapolate back to the case of no misclassification, that is when sensitivity is equal to 1. So this method does it jointly for all the parameters, and it does it both when the factors is measured with error or is misclassified, and it allows for not only one value. I mean, we could also apply it when not only the environmental factor is measured with error, but also if confounders are measured with error, and we could do it with a single step. So I thought to use this because we really wanted to show the epidemiologists and the environmental scientists that this is very easy to apply. There is an R package that is very comprehensive. That said, this method is not optimal. It's an approximate method. We could do better because we have the we have, in certain very simple cases, the bias formulae. So this would do better. But they are less general, because we would like to leave the investigator free of specifying their best model and not having every time to derive new formulae, or sometimes the formulae are not even possible to obtain. But actually, it can be shown that this does not eliminate completely the bias. And actually, we see that it's much more important how you define in the first place the measure and how you measure it, and whether you can obtain replicates and other ways in which you can measure the exposure. It's going to be even more important than using the right method, statistical method. But there's also more work that can be done to improve these methods for measurement error correction. So finally, we applied this method. So hopefully I have some more time to explain how we analyzed the MOBA cohort study. We first conducted the analysis focusing only on the 3 CPG sites that were confirmed across cohorts. Because again, one big thing that is future work is how do we do it in EWAS? So that's what we are working right now. So hopefully I will be able next year to talk about that. So now we are considering just 3 CPG sites. And first we do exactly like Kuppers and Al did, and other researchers. I don't want to point on them, like they're doing the best they can, given the state of the art. And then we add, first of all, how can we improve the measurement? Luckily, in MOBA, they were smart. They did not only rely on self-report, they measured cotinine. And my question to the investigator was, why don't we just use cotinine on the first place? I mean, this is a laboratory measurement. And she said, no, it's not a representation of the long-term exposure during pregnancies, just short-term. I don't feel comfortable. And she really said, no, I prefer the Corson measure. So here we had a lot of debates, I tell you, and then I said, okay, let's reclassify women whose report does not agree with the cotinine result. And actually that was the thing that mattered the most. And then after we have adjusted for cotinine, let's use the method, the statistical methods. So these are just the question we want to address, that is whether we confirm that there is an association between DNA methylation and smoking status, and whether DNA methylation is associated with the health outcome, and whether these CPG sites are strong mediators. So this is basically what we did. We ran the mediation analysis, ignoring exposure misclassification. We improved the classification using cotinine, and then we used the measurement error correction. These are the findings. So in the naive, I call the naive analysis the analysis that ignore misclassification. In the naive mediator analysis, we confirm, yes, DNA methylation is a strong biomarker. Very tight confidence intervals, and we see that smoking leads to hypomethylation, so lower methylated status of these CPG sites on the insulin growth factor gene. So note these are strong effects because methylation goes from 0 to 1. So these are very strong. Here we have the results. So to read the table is a little bit different now because each column now is a different regression where we fit, adjusting for covariates that I excluded now, just for ease of reading, we are adjusting for the CPG site and smoking in the model for the outcome, birth weight. So the outcome is birth weight. We are adjusting for smoking and each CPG sites, and each column is for 3 regressions because we are considering 3 CPG sites. What do we see here? First of all, smoking has a non-significant association with birth weight once we adjust for the mediators. However, the total effect was negative and statistically significant, as expected that smoking induces lower birth weight. Then the CPG sites, none of them had a statistically significant association with birth weight, but large in magnitude. So now, based on our result, we expect that the total effect is underestimated that the direct effect, which is this parameter here, the effect of smoking once we adjust for methylation, we think is underestimated. We think that these parameters, which are already non-statistically significant, are in overestimate. Okay? Now, we conducted the mediation analysis. We used this simple method, and this yields statistically significant indirect effects. So this is the first puzzling thing. We are starting off with the fact that the effect of M on Y is not statistically significant, but we end up with an estimated indirect effect that is statistically significant and explains between 32% and 12% of the effect. Actually, it's statistically significant only for the largest one, and these are not statistically significant. So actually, I will focus myself on this first one, which is strong evidence of mediation, statistically significant, but it is a bit puzzling. If we were to report the regression before, like the parameter for the methylation on the outcome is not statistically significant. So what is it? Is this real? Is not real? Let's see. So let's first reclassify our smoking status using cotinine. What is the result? First of all, from 93, we go to minus 90 around. We observe a much more harmful effect of smoking, as expected. And also in high inflation now of the direct effects. Before it was like 60, 64. From 64, we go to a statistically significant direct effect. Before it was not statistically significant anymore. But although highly deflated, I mean, not that much actually, not that much. Although reduced, it's not that much reduced our indirect effect. So there must be something there. But maybe it's not quite what has been estimated. But it's not statistically significant. So now, once we reclassify, we have less evidence of a mediated effect, but still like tendency toward the mediated effect, I would say. But definitely our conclusion would be much less strong than what we reporting here, when the direct effect is non-statistically significant and the indirect effect is statistically significant, and 30% of the effect is explained by it. Here instead we have still a quite moderate, proportion mediated, but is arising from a non-statistically significant indirect effect, and the direct effect is still statistically significant. So make the investigator much more cautious about the implication of the finding. Yes? Yeah,
just to be sure that 24% is the percentage of the total effect explained by the indirect effect?
Exactly.
Okay. And I guess it's impossible to have confidence interval on that.
So we can, but in this case, since the indirect effect is non-statistically significant, it goes in like in a reasonable value that is below 0%, so I just didn't report it. Yes. Okay. So basically this is the conclusion. Even when we allow for measurement error, the results remain in this line. The more measurement error we allow, the more we see that we get farther from the triumphant conclusion that this insulin growth factor gene is the mediator that explains the effect of smoking on birth weight. But I would not want to say that there's nothing going on. There should be, there could be something going on, but there's definitely a problem of inflation and lack of validity of the indirect effect in this context. So this concludes my presentation, and if you are interested in learning more about the work we are doing in environmental epigenetics and in mediation analysis, I welcome your questions. Of course, there is a lot of future work from here, both trying different methods of correction, using also genetic instrumental variables, and considering high-dimensional settings. But we thought that it's very important to let the people who work in environmental epigenetic be aware of this high risk of presenting false positive findings. Thank you.